Delaware Tech, Chemistry 100, Chemistry 110, Unit 6 continued, Boyle's Law. Boyle's Law deals with the relationship between pressure and volume. So Boyle and his various scientists working with him kept the number of molecules constant. In other words, they sealed the container, and they kept the temperature constant. And they just played around with volume and pressure. And what you know is that when you have a container, and this is showing a diagram of a very simple piston. So the top of this piston can move up and down depending on the pressure that's put on top of the lid of the piston, on top of what would be called the cylinder of the piston. And if you increase the pressure, the volume will go down. And in fact, if you double the pressure shown here, the volume will go down by twofold. You increase the pressure by twofold, you decrease the volume by twofold. Pressure goes up, volume goes down. And the reason why the volume goes down is because you're making it smaller, but the reason why the pressure would go up inside the container is because you're now having the same number of molecules moving at the same speed because the temperature is constant, but they're hitting the walls more frequently because the walls are closer. And because the walls are closer, you're going to get more and more collisions happening for the same period of time, and therefore you're doubling the force against the area of the walls, and that means you're doubling the pressure. So as you increase the pressure, the volume goes down. If you decrease the volume, the pressure goes up. Those mean the same thing, essentially. And then you can do the reverse. If you decrease the pressure, that is, we let up on the piston, well, the piston's going to get larger again. The volume will go up. And likewise, if I made the piston larger by just manually lifting up that lid to go back to our first situation, well, the pressure will go down because there are going to be less collisions hitting against the walls for the same amount of gas moving at the same speed inside the container. So when the volume goes up, the pressure goes down, or when the pressure goes down, the volume goes up. So all you have to remember is that if one of these two goes up, the other goes down, as long as you're keeping the number of particles constant and the temperature constant. So P and V are what we call inversely related or inversely proportional. One goes up, the other goes down, and they go up or down by the same amount. If in this case the pressure is going up twofold, well, the volume is going down twofold. They compensate for each other. So Boyle's law says that pressure times volume is a constant. And this is another way of saying exactly the same thing. Now, this is not a very useful way to use this formula because the constant's going to be different no matter whenever we change how much gas is in our container and we change what temperature we're looking at. So instead, we use a different version of the formula where we use what we call the two-state version of the formula, a before and after set of conditions. If P times V is a constant, then any P times V is the same constant as long as you're keeping N and T constant. You're not changing those things. So that means the initial P times the initial V, or P1 times V1, equals the final P times the final V, or P2 times V2. And you could write this as Pi for initial and Vi for initial, and Pf for final and Vf for final, or you can use the 1 and 2. So let's look at some examples. A sealed balloon is filled with 25 liters of air at 1 atmosphere pressure. Temperature is kept constant. So you already know quite a few things. And let's make a table here to keep track of some of these things. I'm going to pull up my pen marker here, and we'll make a table. We'll have our initial conditions, we'll call them condition 1, and final conditions, condition 2. And you can call it initial and final, or 1 and 2, it doesn't matter. And we have 4 things that can change in all of our gas problems here, P, V, N, and T. Well, in this particular example, we're told it's sealed. Sealed tells us the number can't change. So whatever the old number is, we know it's the same as the new number, so we don't have to worry about that. We're also told that temperature is constant. So the old temperature is equal to the new temperature. So we don't have to worry about that either. We do have to concern ourselves with the remaining two, P and V. And if N and T are constant, and we're only looking at P and V, that's Boyle's law. So Boyle's law asks for those values. Well, we have 3 of those 4 values, and we can solve for the 4th. So let's put them in. We know initially we have 25 liters of air, and it's at 1.0 atmospheres of pressure. Right? Atmosphere of pressure. And we know we're changing the pressure to 1.5 atmospheres. So here is our unknown. V2 is our unknown. This is what we're trying to solve for. Well, we go to our Boyle's equation, which is P1 V1 equals P2 V2, and we solve for V2. So V2 is right here. We see that P2 is multiplying it, so we just divide it on the other side. We put P2 on the other side, and we end up with this new equation. And I'm going to erase those notes on here. And now we have our equation. We have all our values. Our table helps us figure out what's what and allows us to know exactly what each value is. And notice I put all the units in as well. And now we're going to plug them in. P1 is 1.0 atmospheres of pressure. V1 is 25 liters of volume. And P2 is 1.5 atmospheres of pressure. We put this in. The atmospheres will cancel one another, so we don't worry about that. And all we're left with is liters, 16.666 repeating liters. And since we have 2 sig figs here, 2 sig figs here, 2 sig figs here, and we're only multiplying and dividing in this problem, so our rule for sig figs says if all you're doing is multiplying and dividing, you look for the number with the least sig figs, and that's what your answer is. Well, all of our numbers have 2 sig figs, so our answer will be rounded to 2 sig figs, and we'll end up with 17 liters, and that's our answer. I'll clear this, and let's look at another problem. Another sealed balloon is filled with 73 liters of air and at 1.3 atmospheres of pressure. Temperature is kept constant again. What pressure is needed to change the volume to 46 liters? Well, again, if we want to keep track of our parameters, we have our initial conditions, our final conditions, P, V, N, and T. We're told it's sealed. That means N1 equals N2. We're told the temperature is controlled. It's not changing. So T1 equals T2. So we've got an initial volume of 73 liters. We've got an initial pressure of 1.3 atmospheres. And we're changing the volume to 46 liters. So P2 is our unknown. And we use the same equation we did before. PV, the first set, equals PV, the second set. We isolate the P2, so we move the V2 to the other side. And we end up with an equation for P2. And now it's just a matter of taking our numbers out of our table and plugging them in. And you see you end up with an answer. First we're going to cancel the liters, and the only thing left is atmospheres, and we end up with 2.063 atmospheres. That's what our calculator tells us. But we see that we have 2 sig figs, 2 sig figs, 2 sig figs. So again, we need to round our answer to 2 significant figures, and that would be 2.1 atmospheres of pressure.